depending on who you had last semester, or whatever you took one away, some of this Chapter 11 stuff may be familiar, some of it may not, just depending on where they ended up cutting off their semester. So we're just going to kind of skim through it today and Wednesday, and then Wednesday we're going to start Chapter 12, New 12, for the next few days. So Chapter 11 covers intermolecular forces. Alright, so we have what's considered a molecular solid, or a molecular liquid, or molecular gases. These are things that are not ions. Right, they're compounds of some sort. They have covalent bonds in them. And so molecular substances are things that we kind of categorize using melting point, freezing point, solubility. And these properties I'll call it vary. So these properties, those three above, are going to depend on the strength of the intermolecular forces. The intermolecular, I haven't tested my microphone yet to see how far away I can get before it cuts out. So if anyone watches this video later and you're like, hey, you kind of went to nothing there because I walked too far away. I'll figure it out. So intermolecular meaning between two molecules. Right, so it's not within one molecule, it's two molecules interacting together in some way. When we think about intermolecular forces between two molecules and we want to melt, right, we are talking about the fact that these two molecules must have to change their spacing, right? If they're solids, they're really close together, and as they become a liquid, they get farther apart. And so I must have done something to allow them to move apart from each other. Or if I do the other, freezing, right? They were liquids, they were pretty far away, and they've moved closer to each other to become a solid. And so for all of these, the molecules must either gain or lose energy to allow the molecules to change their relative position. Alright, so when we think about melting something, right, you have to add heat in, so you've added heat, molecules have gained that energy, and have moved farther apart. If we think about freezing, we take the energy out of the system, the molecules then come closer together and become a solid. So, if we think about, I'm trying to figure out how to get on my stuff on screen. Like in a dark spot over here in the corner. Alright, this value of energy, the amount of energy either needed, right, if you gain it, how much you need, or if you lose it, how much you lost, that value, the amount. Depends on strength of the intermolecular forces. So if I think about going from a liquid to a gas, right? Let's say I'm boiling something. I'll include that up here, boiling. No, it's freezing boiling. Alright, so if I'm going from a liquid to a gas, the more energy you have to put in to make that phase transition, the stronger the forces must have been to break them, right? So if you are holding hands with someone, playing tag, obviously, playing elbow tag. People just play elbow tag? Maybe not. Okay. Imagine you're playing elbow tag, right? You're hooked elbows with someone else. The amount of energy it takes to break you two people apart when you're playing tag depends on how closely you've hooked each other, right? If you really want to lose your partner because you don't like that person, then you're not going to hold on to them very tightly. That's always my strategy when I play tag and you end up with a slow partner. You want to make sure you're holding on to them loosely so you accidentally lose them, right? And so if it's a strong intermolecular force, then it's going to take more energy to break those two molecules apart in space and become a different phase. So the amount of energy needed depends on the strength. So stronger not talking about boiling. Stronger intermolecular forces, higher boiling point, more energy needed. Alright, so that's all hopefully something you've talked about in other classes. So you may be thinking, man, I really wish I could remember what those intermolecular forces were. Don't you worry. Do a little recapping today. There are 3 types of intermolecular forces that we're going to go through, 3 main ones. First of which being this dispersion force. Sometimes called London forces, sometimes called van der Waals forces, all mean the same thing, they're all interchangeable. Dispersion, London, van der Waals. All molecules have dispersion forces between them. And it comes from the fact that every molecule has the capability of being polarized. They may not all be polar, but there's a chance that you could force them to be polar for like a nanosecond, and then they'll snap back into being nonpolar. So let's say I have nitrogen. Right, nitrogen, we'll say it's a gas. Would normally look like this. Alright, a triple bond and some lone pairs. Based on everything we know about nitrogen, right, nonpolar. There's not an obvious positive or negative end to it. It's symmetrical in every kind of way. So it's a nonpolar molecule. But at any given instant in time, the lone pairs may not be on that nitrogen. They may have migrated over to this one. They may be making a quadruple bond. Right, because as electrons are fascinating, right? As soon as you think you've got them pinned down, they're going to move due to our uncertainty effect, right? As soon as you think you know where they are, they're no longer there because you looked at them, and so they moved because you looked. And so sometimes it's going to look like this. Right, that craziness, or maybe it's going to look like that. And so in both these cases, I have now made an unequal molecule, right? Now I've made this part and that part, something like that. So remember this, does everybody see that little D notation before? Maybe. So I'll back up here. Right, if I have a big triangle, what does that tell me to do in math? Right, change in some sort, right? And so in Greek, that's big delta. Well, little triangle in Greek is this. It's a little d. So if this means big change, this means small change. They both mean change, just this is capital D and this is lowercase d. And so I'm using the little d, meaning tiny change. Instantaneous, non-permanent change. And so in this instant, I now have a positive and negative end, which pulls those two molecules together, and then they'll snap back, and then they'll float apart. And they'll get hooked up to somebody else, and then they'll float apart, and they'll keep changing dipole partners. So the strength of these dispersion forces really depends on two main factors. The first of which is how many electrons the molecule contains. Now I'll do the second one, then I'll talk about why these are the two. Alright, so the second one is the ease with which the electrons can be redistributed around the molecule. So if we think about two different molecules, right here I have a nitrogen gas molecule, altogether has 10 electrons. If I compare that to, there's no periodic table in here, so either you'll have to bring one on a sheet of paper or have a really good imagination as to what the periodic table looks like. But if I compare nitrogen gas to chlorine gas. Right, chlorine, still also nonpolar. Am I showing all the electrons in chlorine, or which electrons do I show in the Lewis dot structure? Right, just the valence electrons. So on paper, they look similar, but really, nitrogen has way fewer electrons, right? Nitrogen's molecular, or atomic number is 7, and so it has 7 electrons. Chlorine's atomic number is 35. So this molecule has 14, and this one has 70. Right, chlorine has 70 electrons. So it has a lot more electrons, and it can redistribute those 70 electrons a lot easier, right? If you had 70 kids, would you know where they all are? Probably not, unless you had GPS tracking on all of them. Probably not, compared to like 14. I mean, it's still crazy, but reasonable, compared to 70. And so chances are, the more gigantic the molecule, the more those electrons are scooting around in space, and easier for it to become a miniature dipole. So, both of these. Let me know if you ever can't read my writing. I get so excited about what I'm talking about that sometimes my handwriting gets a little crazy. So both of these factors increase with molecular weight, right? The overall heavier the atom, more electrons, because weight is related to protons, and protons and electrons are equal, and so the heavier the molecule, the more the electrons. So, our big conclusion. As molar mass increases, the dispersion forces increase, right? Because they're more likely to be a dipole. If they're more likely to be a dipole, they attract other molecules easier. And so the heavier the atom, the increase in dispersion forces. So if the dispersion forces increase, it means the boiling point must increase, right? How much energy you have to put in to pull those two molecules apart must also increase. The bigger the atom, greater the dispersion force. If they're attracted to each other stronger, you got to put more energy in to push those two things apart. Pretty straightforward logic train, I think. So you may be thinking, I wish there was a chart that showed me all numbers, that way you could prove it. Right here, here's my chart. Because you can't be wrong if it's in a chart. I think that's how science works. And so, you can't see that at all. Let's see if I can zoom in. I'm not as familiar with this document camera. Alright, so if I'm looking at the noble gases, Right, so helium has a molar mass of 4 compared to krypton, which has a molar mass of 84. So the mass has increased, so the boiling point has increased. How much energy you have to put in has gotten bigger. Negative numbers are plenty to think about, right? But this is a much less energy compared to this. Or you can look at, this might be easier, halogens, gaseous fluorine compared to gaseous iodine, right? Obviously iodine is much heavier, and it's actually a solid at room temperature, which means you put even more energy in it to get it to become a gas compared to fluorine gas. There you go. Proof. Right? It's in the chart. Therefore, can't be wrong. Questions on any of that so far? Super amazing, right? It gets better, I promise. Alright, let's talk about our second type of intermolecular forces. So dispersion forces are temporary dipoles, which means we're ready to talk about actual dipoles. So molecules with permanent dipoles display what's called dipole forces. Permanent dipoles would be polar molecules. Right? They're asymmetrical in some sort of way, that they have a definite positive and negative end. Dipole molecules do have dispersion forces, but comparatively, they have a lot of dipole force and a little bit of dispersion force. And we line up our dipole forces, right, so the opposite poles line up like magnets, right? So adjacent molecules line up so that you have the negative and the positive in close contact so that they are able to kind of even out that inequality. I haven't talked this much, like in 4 weeks. My throat's like, what are you doing? My husband's a chatty one at home, so I don't get much words in at home, so I try to get them all out here when I'm lecturing. If you've ever met my husband, you're like, yes, that's right. He's a chatty guy. Alright, so if I'm looking at sodium chloride, right, sodium is typically the positive end. Chlorine has all these extra electrons. That's the negative end. So if I'm looking at a molecule of sodium chloride, if I have 2 molecules of sodium chloride, they're going to line up like this. Right, so the chlorine and the sodium kind of are opposite, so the poles even out, which is what's showing over here. This happens to be iodine and chlorine. So you end up with the positive opposite of the negative, and the negative opposite of positive, and they kind of stack in that way. So these are a stronger force, right? It's like a full-on magnet, which is a much stronger interaction than those temporary dipoles that we saw in dispersion forces. Alright, so it's a much stronger interaction than dispersion forces. And so since it's even stronger than dispersion forces, should they need even more energy, or should they use less energy to change states of matter? More, right? Even stronger. So you need even more energy to push these guys apart. So the melting point, or boiling point, right? So it needs even more energy. So if it was just nonpolar, it would be just dispersion, and those are based on molar mass. This, I have dispersion and dipole, so double the force. I need even more energy to get them to change states of matter compared to a nonpolar molecule, which is only dispersion. Let's see if I can read that all in. So to prove my point, I got another chart. So if I'm looking at nitrogen, right? Nitrogen was our nonpolar molecule, and its molar mass is like 28, and its boiling point is negative 196. Well, if I compare that, that's obviously not a huge difference. Carbon monoxide is polar, and so it's going to have dipole forces, so its boiling point, it's only 4 degrees higher. It's not a great example. Okay, the silicon triiodide, hold on. I haven't named molecules in 3 weeks. Hold on. Silicon tetra. Yes, that one. SiH4. That one. Right, its boiling point is negative 112. If I compare it to phosphorus trihydrogen, something like that, pH 3. Its boiling point is negative 88. Let that show how important it is to know how to name stuff. Not super important. Sorry, everyone learns it, and then you realize you'll never need it again. Yeah. Yeah. Yes. No, it'd be the same. Yes, same trend. Yes. Let me think. It would take more, yeah. It would have no, you're right. It'd be a lower freezing point because it takes more energy. Yeah. So, same energy needs, but you need more cold to get it to freeze. No, you need more energy to freeze it because you gotta undo that, how far apart they are to pull them closer together. So this is how I remember it. Boiling point elevation, it takes more energy, so the boiling point is higher than what you think it should be. And freezing point depression, it's a lower freezing point than what you should think it is. We're going to do some math about it, probably on Wednesday, how to calculate what the freezing and boiling points should be compared to what you think they ought to be. It'll be surprising, right? Mm-hmm. And then you're going to do a lab about it. Not this. Next week's lab is freezing point depression. You'll see it in action, stuff freezing. In case you haven't seen it before, it's pretty exciting. It goes from a liquid to a solid. I gave away the ending. But yes, liquid to a solid. Spoilers. I should have said spoiler alert. Turns into a solid. Alright, hydrogen bonding. This is every biologist's favorite type of force. If you didn't have a favorite before, this one should be your favorite. Favorite type of force, hydrogen bonding. Because this is the main type of bonding that occurs in all biological systems, hydrogen bonding. It is technically a dipole force, but it's so unusual it gets its own category. So it's an unusually strong type of dipole force. As the name indicates, you have to have a hydrogen in order to do this. And the hydrogen has to be connected to a nitrogen or an oxygen or a fluorine. What makes fluorine super exciting among a bunch of things? How do we know about its electronegativity? It's the highest, right? It's the highest electronegative, followed by oxygen and nitrogen. And hydrogen is the least electronegative. So you are pairing the least electronegative with the greatest electronegative, right? So you are making a gigantic, gigantic pole. So if I did something like this, HF, right, that's definitely going to be negative. Fluorine. I abbreviate electron. E with a little minus sign. It's my electron. So H is the least electronegative molecule or atom on the periodic table. F is the greatest electronegative atom on the periodic table. You've now stuck them together. So you've made a gigantic difference in electronegativity. So fluorine's going to take the one electron off that hydrogen and pretty much almost leave it like a lone electron floating around. So, so excited, I lost my train of thought. That's not spelled right. Is there an A in there? There's an A right here. I mean, I can spell super for sure. So, hydrogen bonding is super strong. So it's not just like dipole strong, it's stronger than dipole. So it leads to a much higher boiling point or a lower freezing point than you would expect based on the other molecules that are similar to it. Which is awesome because we live on planet Earth, which has a lot of water on it, right? If water froze where we expect it to freeze, the oceans would be frozen all the time. Your body would be boiling, right? Because you're able to maintain your water concentration at less than 100 degrees Celsius, where if we look at the trend of other molecules that are similar, do I have it on this one? No, I don't. If we look at other molecules that are similar, water we would predict it to boil at like 70 degrees Celsius, which means your blood would be boiling all the time. Clearly it's not, hopefully. And so water has amazing ability to maintain its heat concentration without boiling. I could talk for days about water. It's fascinating. But I will save you. I will save you for that. If you take biochemistry with me, we spend 2 whole days talking about just water. I try to keep it to 2. I could probably do 3. Keep it just to 2. Water, just amazing. The fact that it freezes at 0, and the fact that it's actually, as a solid, it's bigger than it is as a liquid. I mean, don't get me started. Fascinating. Alright, what was the one last thing I want to do? Chapter 12. Okay, there's one last fun fact I want to tell you. Alright, the last thing I want to say about hydrogen bonding, because I wrote way too big on the other side. Oh, I was going to do this. Alright, so let's say I have, we'll do water, because I love water. Alright, so here's my water molecule, right? It's nice, bent formation like Lewis structures tell me it should be. And over here, I have a partial positive and a partial positive, which means this is partial negative. Alright, because the oxygen's taking the electron density away from the hydrogen. So if I have another water in the vicinity, I now have this. Right, so they're starting to line up so that this oxygen is attracted to that hydrogen over there using dipoles. And hydrogen being so small allows this oxygen to come in really, really close to share this electron density. And so they'll start to stack up like that. Let's get my colors perfect. Right, so hydrogen bonding occurs when I just circled, those are hydrogen bonds. The hydrogen bond occurs between one hydrogen on one molecule and the oxygen on the other molecule. So this right here, that would be a hydrogen bond, and this would be a hydrogen bond. And you can see, like, I could have another hydrogen bond off of this H or off of those, and they kind of stack up and make kind of a crystalline structure, which is why ice is a crystal, which is why it's bigger than it is when it's a liquid, right? So when you fill up your bucket and leave it outside with the lid on. It could break. That's a terrible example. What I was thinking is, I bought my husband a basketball hoop for Christmas. Right, it has the base that you have to fill with water to keep it from tipping over, and so you have to make sure when you fill it up with water, you leave enough space for when it freezes that the water has space to expand. Otherwise, it'll crack the base open and all your water leaks out. So that's what I was thinking of. I was like, you guys probably have never done that. So maybe you've put a bucket of water outside and let it freeze, or something. I don't know. All right, good. That is the end of today. So bring your chapter 12 notes on Wednesday, and we'll start chapter 12.